Chapter 5 continued, Gases and the Kinetic Molecular Theory, Section 5.3, the Gas Laws and their Experimental Foundations. The properties of gases can be described completely by four physical variables. Pressure, temperature, and temperature will always be expressed in Kelvin, volume, and quantity or moles. These variables are independent of one another. What this means is that we can determine any one of the variables if the other three variables are known. Three key relationships exist among the four gas variables, and these are called Boyle's law, Charles' law, and Avogadro's law. Each one of these gas laws express the effect that one variable has on another variable while holding two variables constant. Since the volume of a gas is the easiest to measure, the gas laws are always traditionally expressed as the effect of gas volume as the pressure, temperature, or amount of the gas is changed. The three gas laws are used to describe a hypothetical perfect gas called an ideal gas using the ideal gas law. An ideal gas is one that exhibits simple linear relationships among volume, pressure, temperature, and amount. Although no ideal gas actually exists, most of the simple diatomic gases such as nitrogen, oxygen, and hydrogen, as well as the noble gases, show nearly ideal behavior at normal temperature and pressure. The first of the three gas laws illustrates the relationship between volume and pressure and is called Boyle's law. Boyle was an English chemist that discovered that the volume of a gas is inversely related to its pressure at a given temperature. Therefore, volume is proportional to 1 over P, or PV is equal to a constant. As P increases, volume decreases, and vice versa. A couple of analogies are: try putting a size 36 body into a size 32 pair of pants. You decrease the volume, you increase the pressure. Also, what happens when you squeeze a marshmallow? You increase the pressure, you decrease the volume. If temperature and quantity are constant, and if PV is equal to the same constant, using Boyle's law, we can determine how changing the pressure can affect the volume of any gas using the relationship where P1 V1 equals to some constant K, which is equal to P2 V2. The constant is the same for the majority of gases. Therefore, if the external pressure of a gas is tripled, the volume will be reduced to 1/3 its initial value. If the external pressure is cut in half, the volume of the gas doubles. A more common way to express Boyle's law is P1 V1 equals P2 V2. The second of the three gas laws is Charles' law. Charles' law is a law stating that at constant pressure, the volume of a given quantity of gas is proportional to the absolute temperature. Therefore, Charles' law states that volume is directly proportional to temperature. Remember that the temperature must be expressed in Kelvin, and to convert degrees C to Kelvin, we add 273.15 to the temperature in degrees C. Also, remember, we do not use the degree sign with Kelvin. So you can look at the ways that volume and temperature are proportional or related on this slide, but the most simplest way to refer to Charles' law is given to you at the bottom of this slide, where V1 over T1 is equal to V2 over T2. If the temperature doubles, the volume doubles. If the temperature is reduced by a factor of 3, the volume will be reduced by the same factor. With both Boyle's and Charles' law, the amount of gas of interest is fixed. What would we observe if the amount of gas of interest is not fixed? To piston A, which is on the left, 0.10 mole of dry ice, which is frozen carbon dioxide, is placed into the tube and is allowed to warm up. As the frozen carbon dioxide warms up, it undergoes a phase change from a solid to a gas and moves the piston up until the pressure of carbon dioxide gas is equal to atmospheric pressure. Notice how far the piston moved. To piston B, which is on the right, double the amount of dry ice that is added to 0.20 moles, and the frozen carbon dioxide is allowed to warm up, which once again moves the piston up. Notice that it moved twice as far as piston A. What this experiment shows us is that if the amount of gas is double, its volumes double. Therefore, at a fixed temperature and pressure, the volume occupied by a gas is directly proportional to the amount of gas in moles. So this is known as Avogadro's law, and it's easily stated as V1 over N1 is equal to V2 over N2. So Avogadro's law states that at a fixed temperature and pressure, equal volumes of any ideal gas contained equal number of particles or moles. No application of the gas laws is more vital or familiar to us than breathing. When you breathe in, the muscles move your diaphragm down and your rib cage out. This is shown in blue on this slide. This coordinated movement increases the volume of your lungs, which decreases the air pressure inside your lungs, which is Boyle's law. The inside pressure of your lungs is approximately 1 to 3 torr less than atmospheric pressure, so air rushes into your lungs. The greater amount of air stretches the elastic tissue of the lungs and expands the volume further, which is an illustration of Avogadro's law. The air also expands as it is warmed from the external temperature to your body temperature, which is an illustration of Charles' law. When you breathe out, the diaphragm moves up and the rib cage moves in, so your lungs volume decreases. This is shown in red. Now the inside pressure of your lungs is approximately 1 to 3 torr more than the outside pressure, so the air rushes out. Chemists use a set of standard conditions in order to study factors that influence gas behavior. This set of standard conditions is known as standard temperature and pressure and is abbreviated STP. The reference condition for a gas under STP are 0 degrees C or 273.15 Kelvin and 1 atmosphere or 760 torr. Under standard condition, 1 mole of an ideal gas is called the standard molar volume. The standard molar volume is 22.4141 liters, or simply 22.4 liters when recorded in 3 significant figures. Bottom line is 1 mole of an ideal gas occupies a volume of 22.4 liters at 0 degrees C and at 1 atmosphere. This figure compares the properties of 3 simple gases at STP. Notice that the mass of the gas and thus its density depends on its molar mass. When we first introduced the gas laws to you, we stated that we wanted to show how changing one of the variables, pressure, temperature, and amount, would affect the volume. We know that Boyle's law focuses on how pressure affects the volume, Charles' law focuses on how temperature affects the volume, and now we have Avogadro's law that focuses on how the amount or moles of a gas affect the volume. We can now combine the 3 individual gas laws into a new relationship known as the ideal gas law or the ideal gas equation. The most common and acceptable version of the ideal gas law is PV equals nRT. We know about P, V, and T, but what is R? R is a proportionality constant commonly referred to as the universal gas constant. The value of R was obtained by measuring the volume, temperature, and pressure of a given amount of gas and plugging these values into the ideal gas equation. The numerical value of R will have units that correspond to the gas variables P, V, N, and T. There are 2 values of the gas constant that are commonly used by chemists. They are 0.08206, or as your book states, 0.0821 liter atmosphere per mole Kelvin, and the other value of R, which we will use later in this chapter, is 8.314 joules per mole Kelvin, where the uppercase J stands for joule, which is the SI unit for energy. If the moles are constant, the ideal gas law can be expressed as P1 V1 over T1 is equal to P2 V2 over T2. This figure makes a central point, which is that the ideal gas law becomes one of the individual gas laws when 2 of the 4 variables are kept constant. When solving gas law problems, keep in mind while they can be stated in many different ways, they normally fall into one of two categories. The first category is where a change in one of the four variables causes a change in another variable while the other two variables remain constant. In this case, you tend to use one of the individual gas laws to help you solve this problem. Units must be consistent and temperature must always be expressed in Kelvin. The gas constant R is normally not used in this category. The second category is where one of the variables is unknown, but the other three are known and no change occurs. Solving problems in this category will be a little easier if you follow a systematic approach such as one given here. Summarize which of the gas variables you know and which one you do not know. Predict the direction of the change and use this prediction to later check your work. Perform any necessary unit conversion. Rearrange the ideal gas equation to obtain the appropriate relationship of gas variables and solve for the unknown variable. Let's work a sample problem that illustrates Boyle's law. Notice right away that this problem involves the volume and pressure of a gas. This is a clue to use Boyle's law. Sometimes word problems can be a little confusing, so I always tell my students to write down what you know because this will help you figure out what you are trying to find. This problem tells us that the initial air in the tube occupies a volume of 24.8 cubic centimeters at 1.12 atmosphere. Therefore, V1 equals 24.8 cubic centimeters and P1 equals 1.12 atmospheres. The pressure is increased to 2.64 atmosphere, which is P2, and the problem wants us to know what the new volume is, which is V2, expressed in liters. We know from Boyle's law that volume and pressure are inversely related. We can use this relationship to predict how this change in pressure will affect the volume. Since we already know the pressure of the gas went up, we can predict that the volume of the gas should go down. Now rearrange Boyle's law and solve for V2. Plug in your values and solve. You are asked to express your final volume in liters, and we are now in cubic centimeters. You can do the math first and then convert cubic centimeters to liters, or you can convert first and then plug the values into Boyle's law and solve for V2. Remember that 1 cubic centimeter is equal to 1 milliliter and that there are 1,000 milliliters in 1 liter. Please work through this problem on your own before moving on to the next slide where you can check your work. Here is the solution to this problem. How did you do? Were you able to come up with the new volume of 0.0105 liters, which is the same as 10 to the 5th cubic centimeters like we predicted? Remember, we predicted that the volume would decrease, and it did. If you had any troubles with this sample problem or with the follow-up problem, please contact me so that I can help you work through this problem. The title of this next problem is Applying the Volume-Temperature Relationship, so we know that this is an example of Charles' Law. You will not always be given the type of gas problem you are asked to solve, so it is very important that you are able to determine which gas law you need to use by the information given to you in the problem. Since Charles' Law involves temperature, please be sure to remember how to convert from degrees C to Kelvin, which is to add 273.15 to the temperature expressed in degrees Celsius. From the problem, we can identify V1 is equal to 1.95 liters and T1 is equal to 25 degrees C. The temperature is changed to 100 degrees C, and we are asked to find the new volume. So what is our strategy? We need to rearrange Charles' Law and solve for V2. We need to remember to convert degrees C to Kelvin. What do we know about Charles' Law? We know that it states that temperature and volume are proportionally related. So if one goes up, the other one will go up as well. Since we know our temperature went up, we can predict that our volume will go up as well. We just do not know how far. Set up your problem and solve for V2, and remember to make any necessary unit conversion. Please work through the problem on your own before moving on to the next slide where you can check your work. So here is the solution to this problem. So what did you find? Hopefully you found that V2 is equal to 2.38 liters and that the volume did in fact increase like we predicted. If you are having any difficulties with Charles' law, please let me know. Remember to work through the follow-up problem before going on to the next slide. From the title of this problem, we know we are going to use Avogadro's law because this is the only law that relates the amount of gas to volume. Again, you may not always be told what gas law to use, so it'll be a valuable tool if you can figure this out based on the information given to you in the problem. Writing down what we know from the problem will help us determine what variable we are trying to solve for. The problem gives us the initial amount of moles and the initial and final volumes. Therefore, we need to solve for N2 and then convert moles to grams. What can we predict for the final amount of moles? We know that Avogadro's law states that the amount of gas and the volume of the gas are directly related. As the amount of gas goes up, so does the volume. From the problem, we see that the volume of the blimp is getting larger, so we can predict that the amount of gas should increase. Please work through this problem on your own before moving on to the next slide where you can check your work. So solving for N2, we should find that the moles of gas does increase from 1.10 moles to 2.31 moles. So our prediction is valid. Now all we have to do is to convert moles of helium to grams of helium and we are done with this problem. So how did you do? Were you able to come up with the correct answer in moles and then in grams? If yes, great job. If no, please contact me so I can help you figure out if and where you may have made a mistake. Now let's work through a problem that applies the volume pressure temperature relationship. Here we have a helium balloon that has a volume of 15.8 liters at 0.980 atmosphere and 22 degrees C. We are asked to find the new volume when the pressure changes to 532 millimeters of mercury and the temperature drops to 0 degrees C. So what do we know? We know V1, T1, P1, P2, and T2. Therefore, we need to find V2. We also know the amount of moles of helium in the balloon does not change, therefore N is a constant. So we need to convert degrees C to Kelvin and convert millimeters of mercury to atmosphere. Do these conversions before moving on to the next slide. Then we need to rearrange the ideal gas equation in order to solve for V2. So let's go to the next slide so we can see how to rearrange the ideal gas equation. So what we have done is to rearrange the ideal gas equation to solve for R. This gives us R1 is equal to P1 V1 over N1 T1, and we can do the same thing for R2. Since the value of R is the same, we can set these equations equal to each other to get P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. Remember we stated earlier that the amount of helium does not change, so the N terms cancel out. This leaves us with P1 V1 over T1 is equal to P2 V2 over T2. Now we need to rearrange the equation so that we can isolate V2 on one side of the equal sign by itself, plug in our values, and solve for V2. Even though the answer is given to you on this slide, it is important that you try to rearrange this equation on your own and do the math. Let me know if you're having any trouble with this problem or with the follow-up problem. Let's work through a sample problem that illustrates the ideal gas equation. This is sample problem 5.6, and it wants us to calculate the pressure of oxygen gas when we are given the volume, amount of oxygen gas, and the temperature. Since we know volume and temperature, we just need to make sure the volume has units of liters and the temperature is expressed in Kelvin. The unit for volume is liters, but the temperature is expressed in degrees C, so we need to convert this to Kelvin. Also notice that we are given grams of oxygen gas and we need moles, so we must do this conversion as well. Once we have completed these conversions, we can rearrange the ideal gas equation and solve for P. Plug in the values for volume, temperature, and moles for the gas and solve for P. The pressure is 1.53 atmosphere. Please work through the follow-up problem before moving on to the next slide and let me know if you have any questions or concerns. Here we have sample problem 5.6, which will allow us to apply the gas laws to determine the correct balance equation for a process. The problem would like us to determine which balanced chemical equation between choices 1 through 4 best represent the reaction taking place in the piston cylinders shown in the sample problem. The problem states that the reaction takes place under constant pressure, and we can tell from the pistons that while the temperature doubles, the volume stays the same. If the amount of gas present, N, were constant, then Charles' law will tell us that as the temperature doubles, the volume would double. Since this is not the case, the amount of gas present cannot be constant. The only way we can observe what is happening in the piston, which is to maintain the volume while holding the pressure constant and have the temperature double, is to see the amount of gas present cut in half. All we have to do now is to look at our 4 balanced chemical equations and see which one has twice as many moles of reactant as product. Try to figure this out on your own before moving on to the next slide. In choice 1, the number of moles does not change from reactants to products, so doubling the temperature will double the volume. In choice 2, the moles decrease from 3 to 2, so doubling the temperature would increase the volume by 1/3. In choice 3, we go from 2 moles to 1 mole, so doubling the temperature would exactly balance the decrease in moles, so the volume would stay the same. In choice 4, the number of moles increased from 2 to 3, so doubling the temperature would increase the volume by more than a factor of 2. So the correct answer is equation 3. Please work through the follow-up problem on your own and let me know if you are having any types of trouble with these kinds of problems.